Hello, this is part one of a two-part instructional video demonstrating how to set up a breadboard with 3 tactile switches, 3 LEDs, and 1 photocell to interact with a range of programming environments on a Raspberry Pi version 2. As a demonstration, here I've written a program in Scratch so that when I push a button on the left, the LEDs begin flashing in sequence. When I push the right button, the LEDs stop flashing. And when I push the middle button, the LEDs flash in a scattered pattern. The Scratch sprite runs around the stage, and then all scripts stop. A breadboard is a way to design the electronic circuits. It lets you connect and disconnect various components like resistors, capacitors, and photocells, all components that come with the Raspberry Pi 2 starter pack from Adafruit. The typical breadboard has gold circuitry underneath that connects the holes on the top in either rows or columns. In this picture I have a mini breadboard turned upside down to see the underside, while the full side breadboard is turned right side up. You can see that there are 2 horizontal rows on the top and 2 horizontal rows on the bottom that connect all the holes the length of the breadboard. Current that flows in any one of the holes in one row can be accessed in any of the holes in that full row. As a common practice, the rows closest to the red stripe running along the full-size breadboard are used for power, while the holes running along the rows closest to the blue stripe are used for ground. But these are only actually put into use as such if we jumper cables to actually apply the power or apply ground. The breadboard itself is really more like a road. We say in real life that a road should have traffic only going in one way or should be only for certain types of vehicles, but in practice it could be used for many different ways. So too with the breadboard. The breadboard also has sets of 5 interconnected holes, a gap, and then a second set of 5 interconnected holes, creating columns along the length of the breadboard. All told, there are 63 total columns of holes, with the gap creating two sets of subcolumns. A current that passes into any one of the 5 holes in a subcolumn can be accessed by any other hole in that subcolumn. The subcolumn gap structure is a very useful design. For instance, let's connect up the cobbler to a breadboard. Adafruit has created this cobbler by combining a receptor for a 40-pin plug, a labeled printed circuit card so that we know which pin is associated with which GPIO or general purpose input-output on the Raspberry Pi, and then 40 pins designed for a solderless breadboard like the one that comes with the starter pack. The pins of the cobbler are spaced to connect to subcolumns on either side of the gap of the breadboard. The labels help us to identify the proper pins, and so will be useful as we move forward. The pins on the cobbler labeled 5V and 3V3, or 5 volt and 3.3 volt, are pins 1 and 2 on the Raspberry Pi 2. I've connected those pins to the holes at the very edge of the breadboard to the left of the column labeled 0. Make sure that the pins are all properly aligned with holes on the breadboard. Then push firmly down so they are all well seated. Before we go further setting up our breadboard, let's look at the other components of the starter pack. In particular, let's look at the bonus parts on this list. A photocell senses the amount of light reaching the cell. The tactile switch, when pushed, draws down current, thus changing the input from 1 to 0. The LEDs light up when current is applied. A capacitor acts like a tiny battery helping to smooth current input to a component, among other things. A resistor is used to reduce the amount of current flowing to a component. Think of how a nozzle on a hose, a garden hose, might be used to provide a trickle of water to a plant, or provide a jet stream of water to clean off a surface. Ohm is how much the current is restricted. So a 560 ohm resistor that comes with the starter pack is more like a jet stream setting on the nozzle, while the 10K or 10,000 ohm resistor is more like a trickle setting on a water garden hose nozzle. To distinguish one resistor from another, you need to learn how to read the color stripes on the resistor. Charts are available to decipher the code. Resistors come with 4 or 5 strips. Ours has 4, so we'll look at the first band, the second band, and the multiplier band. For the 10K resistor, the first band is brown, or 1. The second band is black, or 0. The third band is orange, or 1K ohm multiplier. This lets us know that the resistor is 1, 0, and then 4 more zeros, or 10,000 ohms, or 10K ohm. On the other hand, the 560 ohm resistor has a first band of green, or 5, a second band of blue, or 6, and a multiplier band of brown, or 10 ohm. This lets us know it is 5, 6, 0, or 560 ohm. In each case, the final band is the tolerance and just lets us know how precisely at that value it is. In most cases, the tolerance doesn't matter that much. In our case, it certainly doesn't. So we're not going to really worry about that band. So with this background behind us, let's begin hooking things up. First, let's put 3.3 volts of power to the power rail of the breadboard and ground to the negative rail of the breadboard. We'll do this by connecting a red jumper to the hole in the subcolumn associated with the pin of the cobbler labeled 3V3, and connect the other end of that red jumper to the row next to the red stripe. We'll connect a black jumper from the hole in the subcolumn associated with the pin of the cobbler labeled GND, or ground, and connect the other end of that black jumper to the row next to the blue stripe. There's nothing magical about the different colored jumpers. One is the same as the other. But sometimes color coding can help to identify what that cable's use is by a quick glance at the color. And in my mind, those colors make sense to me. Feel free to choose the colors that make best sense to you. Next, let's connect up the tactile switches. These have 4 silver legs coming out of the bottom of them. They only line up with the holes on the breadboard reaching across the gap in one orientation. Align them carefully, as I found that it's very easy to bend one of those legs underneath the switch instead of going into the hole if they're not perfectly aligned. Once you're comfortable with the alignment, push down firmly to make sure the legs go all the way into the holes and make good contact with the track underneath. Connect up the 3 switches in line with each other. I left a gap of a couple of holes between each switch to make it easier for me later to press one button on this one switch without hitting the button on another switch. Indeed, you'll find that breadboarding itself can become as much of an art as anything, and personalities begin to shine through in their layout. Some are especially anal about alignment, right angles, and such. It's worth taking care, whether or not you're that anal about it, to make sure that things are aligned in ways that everything can remain firmly seated even while you're working with components. Because realize nothing is permanently attached to the breadboard. That's the beauty of it, but that's also the danger of it. You also want to make sure the wires aren't becoming tangled, and that bare wires like the legs of the LED or the wires on either end of a resistor don't touch one another and inappropriately allow current to cross between. So speaking of the LEDs, let's connect them to the breadboard next. One leg of the LED is slightly longer than the other. The shorter leg will get connected to the blue ground rail, while the other one gets connected to its own subcolumn of pins. Connect each of these up, leaving a couple of subcolumns between to avoid the legs of each from ever accidentally touching. The GPIO, or general purpose input-output pins of the Raspberry Pi, include 26 pins that can potentially be used for either input or output, and they can be programmed to be either one or the other. When programmed to be an output pin, they provide sufficient current to power one LED, but the LED requires a 560 ohm resistor between that current and the positive leg of that LED. So let's connect one leg of the 560 ohm resistor to a hole in the subcolumn associated with the LED, and the other leg across the gap in a nearby subcolumn. The subcolumns don't have to be right across from each other, but again, here's where that art and right angles can come in for the more precise of us. I chose to use then red, green, and blue jumpers to be associated with the red, green, and blue LEDs respectively. I connect the blue jumper/LED to pin 5 as labeled on the cobbler. I connect the red jumper/LED to pin 6 as labeled on the cobbler. And then I connect the green jumper LED to the pin labeled 13 on the cobbler. You can use any of the numbered pins, but I like the feel of those 3 contingently labeled pins on the cobbler. It just had a sense of rightness to me. Now, to wire the tactile switches. I chose gray or white jumper wires to go between one silver leg of each switch and the ground rail. I used yellow, purple, and red jumpers to connect pins 17, 27, and 22 on the cobbler, essentially giving me an orange button, a purple button, and a red button. The other end of those jumpers connect to silver legs on the opposite corner of the switch to the ground connection. This needs to be opposite both as in on the other side of the gap, but also on the top or bottom of the switch. It doesn't matter which corners are used as long as they are opposite. In this picture, notice that the top 2 switches have the ground in the bottom left corner and the input jumper on the top right corner. The bottom switch has the ground in the top left corner and the input jumper on the bottom right. Either way works okay. Here then is what our connection looks like so far on the cobbler. There are jumpers connected to the pins labeled 3V, 17, 27, 22, 5, 6, and 13 on one side of the cobbler, and to GND or ground on the other side of the cobbler. Last, let's hook up the photocell. First, we'll need the capacitor that came with the starter pack. The shorter leg of the capacitor is on the same side as the silver negative label on that capacitor. Connect that to the ground and then connect the other leg to one of the unused subcolumns. Connect one leg of the photocell to that same subcolumn and the other leg to an unused subcolumn on the other side of the gap. Plug in a jumper to the subcolumn with the capacitor and put it in between the capacitor and the photocell. Connect the other leg of the photocell to the 3.3 volts. And the picture shows you how to hook these last little bits up. So here's a look at the final product. And here's also a listing of the pins and associated components for reference. All that's left to do now is to connect the cobbler to the Raspberry Pi itself. The picture has oriented the Pi so that its GPIO pins are in the same orientation as the cobbler. That is, pin 1 on the cobbler and pin 1 on the Raspberry Pi are both to the right. The black ribbon cable has a gray stripe on it. This is meant to indicate pin 1 on the black ribbon cable. Orient the cable so that the gray stripe is on the right side as well. Connect it to both the cobbler and the Pi, and firmly seat each end. Voila! You're ready to begin programming. That concludes part 1 of this instructional video. In part 2, we'll use Scratch to test and then read and control the switches and LEDs.